thank you. I wanted to present a little project we developed when I had the joy to be on an archaeological excavation. I'm not an archaeologist, I'm a geographer doing a PhD on landscape evolution and development. And I was working in South Africa with the archaeological team of Conard at Sibudu Cave, which is a paleolithic site. And yeah, the area is eastern southern Africa. You see here the port of Durban, and this is the Indian Ocean, and the area is up to the mountain range of the Drakensberg area. Semi-humid conditions, very moist. Yeah. The thing is, we wanted to find out. You see that there are a lot of sites on the southern coast of southern Africa, but there's a lot missing in the eastern part. This is a query from the road database, the Rocky project, the project I work for, developed for over 10 years now, which has, I think, 3,000 or 7,000 sites from the Pleistocene, with assemblages and cultural data and ecological data and all that stuff, just to make a bit advertisement. And all these sites were occupied during the two seasons of Stilway and Hosen's Port, 70,000 years ago to 60,000 years ago. And yeah, they're missing sites. And now we wanted to map where we can maybe find additional sites. The three known sites there are all rock shelters, which means that they are have a very good preservation. You can see here that they have a very fine stratigraphy of thousands of years. And but what is much more interesting is how they were formed. You have the cyclical incision of rivers in that area, where you have lateral erosion, which undercuts the slope and forms a cave. And then you have sea level low stand, which makes the river incise vertically and abandons that old river course, which leaves behind these rock shelters. And they are very good for site preservation because it's safe from flooding because it's above the stream level, and you have rockfall topplings that save your sediments from erosion. We then used a pretty simple or pretty typical workflow for machine learning. First, you need a sample. We did a geomorphological map of the area surrounding Sibudu. And then we tried to get the attributes of these samples, of these rock shelters we mapped. First of all, of course, topo indices, but then also later hydromorphologic and lithological information. Put that in a predictor set, and then made a feature reduction, mainly based on expert knowledge, but also on statistical correlation, to get the factors that are important for these sites. So we used a high resolution radar elevation model, which is 13 meters, which is high resolution for radar, but of course not for LiDAR. But it has a very large extent. It's a worldwide data set, which covers our 200 kilometers along the coast. We calculated some topographic indices, the local ones, typical ones, slope, curvature, openness, visibility, and so on. We also did some regional, like valley depth or elevation, vertical distance to channel network, hydrological indices, morphological indices, And we also categorized the landscape into landform classification, topographic position index in that case, or curvature classification, just to quantify the landscape. And the challenge is now to distinguish a slope like this. So we can't really see the rock shelter because it's a 2.5D model and not a 3D model. We can't look into the cave, but we can get the features a rock shelter has seen from above. To distinguish the slope, maybe this slope from the rock shelter from this slope that is structural and that formed by river erosion. So we had all these predictors and put them in the model and got not so good results because more or less half of the map was predicted as a rock shelter, which makes no sense. So we decided we needed more predictors and leave all the ones behind. And we had a look at the geomorphological processes that form these rock shelters. I already mentioned that they are formed through fluvial bank erosion. And interesting thing there is they are confined meanders. So they cannot roam or meander freely, but they are more or less bound to a certain course that was already set before the Pleistocene. And then now they make incision and only very low lateral variation. Therefore we use two indices. One is the stream power index, which is composed of the catchment of each single cell. So the amount of water that is flowing into that cell and the slope, which gives you an idea about the speed of the water. So you can estimate the erosive power with this index. And we had a look at the sinuosity. You see here, the sinuosity, it's defined as the way a river flows between 2 points compared to the Euclidean distance, or the direct line between those points. And if you have there, for example, a sinuosity of 3, then it means that maybe 2 points are 1 kilometer apart by Euclidean distance, but in that area the river flows 3 kilometers. And at these places you have higher bank erosion. Here you see Sibudu Cave, and it also has a value, I think, of 2. So these green to yellow areas show us the places where we have increased erosive power. And then we also have the geology. So the interesting thing is you have predominantly sandstones and some granites that are able to form rock shelters. Others, like mudstones or shales, strictly collapse if you undercut the slope. So you can't have rock shelters there. We use that. And another thing is these other surfaces, lithologies, are very deeply weathered in that area. So they're all prone to erosion, and even if you had artifacts there, they are not preserved. They are mobilized and maybe somewhere in the Indian Ocean. So we also got rid of some predictors we thought it might be useful, but then didn't. One is the distance to the shoreline. You see that Umhlatutana, Umbelibeli, Sibudu, they're all pretty close to the coast. But first of all, here we see that in the time when it was occupied, sea level was 60 meters lower. They were, which is about this. So the distance to the coast was far longer, and there is not really evidence for coastal adaptation of these sites, because there are, for example, shells in that site, but they think that they are were not used for consumption, but more for cultural reasons. So it was more or less the coast was not in their daily foraging distance, or just not in their lifestyle. And we also got rid of the distribution of lithic raw materials, just because you have these intrusions everywhere. So the lithic materials are everywhere. You don't have to select any areas. And we also got rid of some highly correlated variables just for feature reduction, because if you see here that mountain set max in elevation or vertical distance to channel network is very highly correlated to the topographic compound index, they just give no further information. There's no information gained for the models from these indices, so we just got rid of them. And we trained a maximum entropy model, which is based on the presence data we got from the geomorphological map, and a background sample, not absence data, but a background sample, and it just compares the attributes of our samples to that of the background and looks where they are very specific. And these attributes are very important, have an important contribution to the model, and the response curve, and that's how you model the suitability. It's not called a probability, but the suitability for some mathematical reasons I don't understand. And we also use that model because it's capable to use both numerical and categorical data we wanted to use. And here you see the map we created. You see that there are about 500 potential rock shelters in that area. What is quite nice that they are more or less concentrated, so you can easily go maybe into that part of that valley and sample them within 1 day or two. Matters how detailed you want to do it. And the sites are attributed with the suitability, and you have all the information that came from the topographic indices. And this year we also did a validation campaign in that area earlier this year, where we sampled 2 rivers, one south and one north of the Tongati, the river of Sibudu Valley. And we found that some weren't accessible, some weren't existent. We found a lot of outcrops, and 2 of them were actually rock shelters. And we started also to dig there. We found this pottery. I have no idea how old it is, but it's still too young for the research of the archaeologists digging there. But they told me I should stop digging when I find this stuff, because I might destroy their stratigraphy again. And this was quite a nice result, because it showed that it can keep the sediment, can keep the archive. There were also rockfall on top of the sediment, which was already weathered. That was for us an indication that the sediment below must be a bit older. Just to conclude, the site prediction was made for that specific region. If you go to another region, you have to find completely different parameters. It helped a lot to speak with the archaeologists and run the model again and again with different predictors to find which one are really interesting, and have a look at the model, at the performance of each predictor and the response curve. And the challenges are, as I already mentioned, that you have a 3D landscape derived from a 2.5D terrain model. And yeah, the next step would be to distinguish the rock shelters from the outcrops. Thank you.